how matter learned to reassemble itself. At first, it looked like a trick, broken materials repairing their own structure without tools, glue, or human intervention. But what scientists were witnessing was something far stranger. Matter was learning how to put itself back together. To understand why this matters now, we need to revisit how materials have always behaved. When something breaks, it stays broken. Entropy wins. Structures decay. From cracked bridges to worn electronics, civilization depends on constant repair. Waste is the price of progress. The modern world exposed the cost of that assumption. Infrastructure aged faster than it could be maintained. Devices were designed for replacement, not longevity. Resources drained while systems grew more complex. Engineers began asking a radical question. What if materials could sense damage and respond on their own? The answer emerged from the intersection of chemistry, physics, and biology. Researchers studied how living systems heal. Bones remodel. Skin regenerates. Cells repair molecular damage continuously. These processes were not magic. They were chemical rules executed locally without oversight. By embedding similar principles into synthetic materials, scientists created structures that responded to stress. Microcapsules rupture when cracks formed, releasing repair agents. Polymers realigned under heat. Metallic lattices reorganized at the atomic level. Damage became a signal, not a failure. At first, the effects were modest. Hairline cracks sealed. Minor where it disappeared. But each iteration grew more capable. Materials began restoring strength, not just appearance. Some systems could repeat the process multiple times without degradation. This marked a fundamental shift. Materials were no longer passive. They were responsive. They carried instructions for their own survival. And once matter could reassemble itself, the line between structure and system began to dissolve. As self-healing materials improved, their behavior grew more sophisticated. Repair was no longer limited to closing cracks. Structures began redistributing stress, altering internal geometry to prevent future damage. Matter was not just fixing itself. It was learning from failure. This adaptability came from decentralized design. Instead of a central controller, materials relied on countless local interactions. Each region responded to its own conditions, guided by embedded rules. Together, these responses produced global stability. The implications spread quickly. Aerospace components repaired microfractures mid-flight. Electronics restored conductivity after damage. Protective coatings thickened where exposure increased. Systems once fragile became resilient. But the conflict emerged when reassembly crossed into reconfiguration. Some materials began altering their shape or properties based on use. A bridge could stiffen under heavy load, then relax when traffic eased. Armor could harden where struck and soften elsewhere. Structures became situational. This challenged engineering culture. Predictability is safety. Materials that change behavior introduce uncertainty. Certification systems struggled to keep up. How do you approve a structure that is not the same tomorrow as it is today? Cost added another tension. These materials were expensive and complex to produce. Scaling them required new manufacturing methods and supply chains. The promise of durability collided with economic reality. Yet progress continued. Failures decreased. Lifespans extended dramatically. Waste declined. Maintenance shifted from constant repair to periodic monitoring. The math was hard to ignore. The deeper shift was conceptual. Matter was no longer defined by fixed properties. It was defined by processes. Strength, flexibility, and durability became behaviors, not traits. And that forced a reconsideration of what it means to build something permanent in a world designed to change. The conflict reached its peak when reassembly became autonomous. Some materials no longer waited for damage to occur. They anticipated it. Sensors embedded at the molecular level detected stress patterns and initiated restructuring before failure happened. This predictive behavior blurred a line engineers had never crossed before. Materials were making decisions, not consciously but functionally. They prioritized certain regions, sacrificed others, and optimized for long-term stability over immediate appearance. In critical systems, this raised alarms. Infrastructure that adapts on its own can drift away from its original design parameters. A structure that evolves over time may outperform expectations, but it may also behave in ways no one predicted. Accountability became unclear. If a material chooses its own configuration, who is responsible for the outcome? The concern deepened in military and security applications. Self-reassembling armor, vehicles, and drones promised unprecedented resilience. But systems that heal and adapt are harder to disable, harder to inspect, and harder to control. Durability began to look like persistence. At the same time, researchers saw opportunity. These materials thrive in environments where maintenance was impossible. Deep space, the ocean floor, disaster zones. Structures could endure extremes, recover from damage, and continue functioning long after human oversight ended. The emotional peak came when long-term tests revealed something startling. Given enough cycles of damage and repair, some materials improved. They became tougher, more efficient, more resistant than their original form. Failure was no longer a cost. It was information. Matter had crossed a threshold. It was no longer static. It was experiential. And once materials can learn from the world they inhabit, the future of construction, technology, and resilience changes forever. The resolution emerged through restraint and design. Engineers learned that self-reassembling matter did not need unlimited freedom. It needed boundaries, guided adaptability, rules that allowed learning without losing intent. Standards evolved. Materials were designed with memory limits, reset points, predictable ranges of change. The goal was not evolution, but resilience. Systems that could recover without becoming unrecognizable. The broader impact was quiet but profound. Cities imagined infrastructure that aged gracefully instead of collapsing. Products shifted from disposable to durable. Repair became an internal function, not an external cost. This did not eliminate decay. It redefined it, where it became feedback. Damage became data. Materials participated in their own survival, rather than resisting it blindly. At a deeper level, the science challenged a long-held belief that order must be imposed from above. Self-reassembling matter showed that stability can emerge from local rules, repeated patiently over time. The world did not suddenly become unbreakable, but it became less fragile, less wasteful, more forgiving of stress and error. How matter learned to reassemble itself was not just a technical achievement. It was a philosophical one, a reminder that systems designed to listen can last longer than systems designed to resist. So, what do you think? Should our technologies learn the way living things do, or is some fragility still worth preserving?